All right, so yesterday I was talking about simplifying graphed neural network SGN. But now today we have another title. We have simplifying clustering with graph neural networks. This paper in 2022 by Bianchi. The objective functions used in spectral clustering are generally composed of two terms. A term that minimizes the local quadratic variation of the cluster assignments on the graph, and a term that balances the clustering partition and helps avoiding degenerate solutions. This paper shows that a graph neural network equipped with suitable message passing layers can generate a good cluster assignments by optimizing only a balancing term. Results on attributed graph datasets show the effectiveness of the proposed approach in terms of clustering performance and computational time. So you know about spectral clustering that this balanced K-cut objective is just a ratio of two set functions. So B hat is a set function that balances the size of the clusters in the partition. So depending on the choice of B hat, one obtains different cuts such as ratio cut and normalized cut. This numerator can be expressed in matrix form. To see that, first one rewrites the cut as this sum. Because zi, zj, they just take one of the values, either -1 or 1. Then if you write there, then if you simplify it, you get the same thing, and L is the Laplacian. The relaxation done in spectral clustering to handle the discrete optimization problem is this one. Besides the graph Laplacian, other operators matching the sparsity pattern of adjacency matrix can be used. One of such operators is the symmetrically normalized Laplacian. We generally use a different partition as the edges to be cut are weighted by the degree of their end nodes. The term S transpose LS measures the local quadratic variation of S on graph, which is the quadratic variation of S across adjacent vertices. Laplacian smoothing minimizes LQV by making similar the elements S sub I and S sub J if nodes I and J are connected. When using L sub S, the LQV is this one, S transpose LS. So a basic message passing layer for graph neural network can be seen like this. And A tilde is an operator matching the sparsity pattern of A, and sigma is a nonlinearity. So look at this one, and now we go to clustering with GNNs. Min-cut pool is a GNN layer that computes soft cluster assignments. So it's just unlike if you remember diffpool, they had another GNN, but min-cut pool, as I explained in a different video, it was just the softmax of multi-layer perceptron. So it's very simple to obtain S. So K is number of clusters. It is fixed in advance, and that's why everybody likes this algorithm. Not because of that is fixed, because it is easily seen that is differentiable. And the algorithm, is differentiable. You can use backpropagation, easily justified mathematically. So X bar are node features generated by a stack of one or more message passing layers. And the softmax ensures S is a proper cluster assignment matrix, because this is the nature of softmax. The sum should be 1. So to learn the cluster assignments, Minkut-Pool optimizes the following unsupervised loss, if you remember. The first term minimizes the LQV, linear quadratic variation, while LB, L sub B is balancing term. This is balancing term that helps prevent degenerate solutions. Compared to problem 2, the LQV in the balancing terms are summed rather than taking the ratio. This helps both to prevent numerical issues when L sub B gets too small and to keep L sub MC in a controlled range, which is desirable when the GNN must also minimize other losses. Similarly to Minkut-Pool, Daemon optimizes a loss composed of linear quadratic variation and a balancing term. The term L sub M pushes strongly connected components to same cluster, while L sub R is a regularization term that penalizes the degenerate solutions. So the cluster assignments S can be optimized by minimizing this. The proposed loss simplifies L sub MC and D M considerably, as it consists only of a balancing term. Such a simplification offers the following advantages. They added this is the added value of this paper, just because the computational complexity is reduced, as less operations are needed to compute L, and fewer competing terms in the loss can ease the training and speed up the convergence. This was one of the things that the article Daemon were criticizing them, saying that your algorithm is too slow is not non-smooth for training of large graphs. So maybe this was the motivation of their paper. This paper is the motivation to answer them that no, we can have fewer competing terms in loss if we just use this as an extra loss. So despite its simplicity, the proposed, of course the third one is very important. There are no ratios in L, which could cause numerical instability during training. So they understood their weakness, and now they covered it very quickly. Excellent paper. Despite its simplicity, the proposed loss can still yield an optimal clustering assignment. The key insights that motivated its design are presented in the following. The absence of LQV term in the loss is compensated by the presence of message passing layers that generate the features used to compute the cluster sign. So the following message passing layer can be used. Now, this A tilde is an operator matching the sparsity pattern of the graph, and delta is a hyperparameter. When delta is 0, the node features are not aggregated with those of the neighbors, and the message passing layer becomes equivalent to a dense layer. The message passing layer minimizes the linear quadratic variation of the node features. To minimize linear quadratic variation, we first compute the derivative with respect to ith component. The whole gradient is given by this. The following update minimizes the linear quadratic variation of the node features with gradient descent. And delta indicates the gradient step. Clearly, there is a difference in minimizing the LQV rather than LQV of S. Nevertheless, being phi a smooth function, if two node features are similar, they will likely to map into smaller assignments. So the purpose of balancing term is to encourage a partition where the nodes are assigned with high confidence to only one cluster and the number of elements in each cluster is approximately the same. And they have a theorem that the optimum of this trace is a balanced partition with cluster of size n over k. And they use this cluster accuracy and H maps hard cluster assignments to the best matching class. And for PubMed, for example, this accuracy that we discussed, this cluster accuracy that we discussed, for diffpool is 0.41. But for Mincut, now it is even better than Demon. Demon criticized them in one paper. Now they have slightly better performance. Even for other data sets, we see some improvement from Demon to Mincut.